Hi students, welcome in chemistry classes. I am Priyanka Jain and you are watching the videos of thermodynamics. In our last lectures, we have studied about the heat capacities, heat capacity at the constant pressure, at constant volume, different type of relationships, enthalpy and internal energy. These whole topics we have cleared and we have seen the numericals based on that. Okay, I think you have seen that videos and we hope that you like that videos. Okay, so if you are liking my videos, please share these videos and please like and comments. Okay, so let's start our new lecture that is on the isothermal processes. The next thing that we have to study is the different types of the processes. It means isothermal processes, adiabatic processes. What is asked to you? You have to find out the values of del U, okay, or you have to find out work done, or you have to find out the heat involved in the process, or you have to find out del H. These four things you have to find out. These are your questions. Okay, you have given the processes. It means if the process is isothermal or the process is adiabatic, you have given, and you will have to find out either the internal energy change or work done or Q or the enthalpy change. Okay, so see here, for this you will have to find out three things. First of all, you will have to find out the work done. Okay, and then you will have to find out the internal energy. Once you know these two things, you can find out the value of Q by the first law of thermodynamics. Okay, from the first law of thermodynamics, we know that the Q plus W is equal to del U. Okay, so if we know W and if we know the internal energy, then we can find out Q, right? And then the remaining thing is the enthalpy change. So if we know about the internal energy change, then we can find out enthalpy change. Okay, so we will see all these things one by one. Okay, we are going linearly and we will see all these topics. So first of all, we are starting with the work done. Okay, work done we will have to study both in the isothermal process as well as in the adiabatic process. Okay, so first we are seeing work done in the case of isothermal process. See here, we know isothermal process may be of two types. One is reversible and another one is irreversible. I have told you about these two processes in my previous lecture, but a little bit we are seeing here. See here, reversible processes means if suppose we are taking a cylinder like this is our system, okay, and this is the piston, okay, and if we are doing the process in such a way that it is going in the infinitesimally steps, it means suppose here we have put on the pressure, okay, and we have to reduce the pressure, okay, we want to reduce the process, then we are doing it by a little amount. It means one by one, a small point, then a small point. In this way, we are lifting the weight. Okay, a particle, another particle, second particle, third particle. In this manner, we are removing the pressure from this. Okay, so the process is going in the infinite steps, and in each step, the process will be reversible. Okay, in this manner, this process in each step will be reversible like this. So such a process is called the reversible process, but actually no one process is reversible. This is only the theoretical thing that we are studying because we will have to find out the ideal t. First of all, we want to know what is the ideal thing. Okay, so we are studying the reversible processes, but actually there is no process that is reversible, just we are studying it. Okay, so that we can find out how much we can make a irreversible process like a reversible process. Okay, so see here, irreversible process, all the natural processes are the irreversible. It means suppose we are taking a gas cylinder, okay, and here is the pressure, this is the piston, and here is pressure. Now we want to decrease the pressure, so we can do it in one step or in two step or in three step. Okay, it means we are supposing here the pressure is 3 atmosphere, okay, and then we are removing some of the pressure and then we are doing it to 2 atmosphere. Okay, so our piston now goes here. Okay, then again we can reduce the pressure and we can remove some of the weight and it is coming to 1 atmosphere. Now our piston will be here. Okay, so in this manner when we are doing the process, This is called irreversible because there is no step that is like a reversible process. Okay. So first of all, we will have to find out the work done in a reversible isothermal process, then in the irreversible process. See here, whenever we see the reversible isothermal process, if we are looking at the external pressure, then here in this case, external pressure is approximately equal to internal pressure because we know that each step is an equilibrium. Okay, each step is an equilibrium. There are several steps and each step is an equilibrium. So our internal pressure is almost equal to external pressure, and this is called the pressure of the system. Okay, one thing that you have to consider here. And here the W, it means work done, is we know is given by the integration of P external dV. Okay, so this external pressure is now not constant. This is almost equal to P internal and this is called the pressure of system, but it is not constant. So we cannot take this term outside the bracket. We cannot do this. Okay, so this will be written like integration of PdV. Okay, but in the case of irreversible processes, when we are considering the irreversible process, our external pressure is constant. The pressure that we are putting here from the outside is constant. It can be 1 atmosphere, it can be 5 atmosphere, anything, but it is constant, we know. Okay, so here in this case, W is given by minus integration of P external dV. Now this term is constant, so it can be drawn outside this integration. Okay, so we can write minus P external and integration of dV. And now what will be the value of dV? That will be equal to V2 minus V1. So we can write W is equal to minus P external V2 minus V1. Okay, this is a general thing that we are seeing about the reversible and irreversible processes. Okay, now we will consider both of these terms one by one. Okay, so see here. Alright, now see work done for an ideal process in isothermal reversible process. As we know, reversible process is an ideal process and we are taking here ideal gas. So whenever we are seeing the ideal gas, one thing you should remember, we are using here the ideal gas equation. It means PV is equal to nRT, or we can say PV is equal to constant. Okay. So one thing you should remember, whenever you have given PV is equal to constant, it means we can use here the term P1 V1 is equal to P2 V2 and this is equal to nRT. Okay, so whenever you have not given nRT, then you can use P2 V2 or you can use P1 V1. One thing is clear? Okay. Now see here, work done for an ideal gas in isothermal reversible process. See here, first of all, the basic thing that you should understand, what is an isothermal process. Isothermal process means any process in which the temperature is constant throughout the process. It means dT is equal to constant. Okay. Now one thing you should clear here, that dT is constant. Okay. We are not saying that del T is constant. These two are the different things. Whenever we say del T is constant, it means T2 minus T1 is equal to constant. Okay. And it means that the final and the initial temperatures are same, but we cannot say that the process is constant throughout the process. It may happen that sometimes the temperature is increasing and then sometimes the temperature is decreasing, and ultimately it is going from the initial to final state at the same temperature. It means initial and final temperatures are same, but the whole process is not at the constant temperature. Okay, so this thing cannot be verified by a isothermal process. An isothermal process says that dT is constant. It means at each and every step of the process the temperature is constant. Okay, now see here, when the process is isothermal, PV is constant. Okay, so dT is constant, but P is not constant. Okay, this thing you should remember. as I have told you earlier that P is constant. Okay, so we can say P is a function of volume, or we can write here P is equal to nRT upon V. Okay, so you can use this equation, or this equation, any one equation whenever you are using it for the numerical. So find out the value of W, work done in an isothermal process. See here, we are seeing the expansion case. Okay, we are seeing expansion case. It means this is our cylinder and this is the piston and here is a gas field. Okay, now suppose this gas is at the V1 volume. Okay, and we are doing the expansion. It means now the piston is going from here to here. Okay, it means the volume is increasing from V1 to V2. Okay, so the pressure is going from P1 to P2. It means pressure is decreasing and volume is increasing. Expansion. And we know that the expansion work is always negative. So what we will write here? W is equal to minus integration of P dV. Okay. See here, you will have to use always the minus sign. Okay. Either expansion or isothermal. This formula always gives you the value. Either the process is expansion or it is compression. Both you will find by this formula. You does not need to put extra signs. Okay. So here the formula is W is equal to minus integration of PdV. Okay. Now we can write here in the place of P what? nRT upon V dV. Okay. So this nRT is a constant term, so it comes outside and we are getting V2 to V1 integration in the limits V2 to V1 dV by. So what we are getting? Minus nRT natural log of V2 upon V1. Okay, or you can write W is equal to minus 2.303 nRT logarithm of V2 upon V1. Okay, so this is the general formula for the isothermal reversible expansion of the ideal gases. Okay, as we know that V2 is greater than V1. In the case of expansion, V2 is greater than V1. So this term will be positive. Okay, and when this term is positive, we are getting a negative sign. It means the process is expansion. Whenever we have given the compression process, then this formula will automatically change the sign because we know V2 is lesser than V1. Then this term will be negative. Okay, this term will be negative. So this whole term gets positive. Okay, so just you will have to put only the value of V2 and V1. You will automatically get the sign here. Okay. So this is the formula for the isothermal reversible expansion or compression work done in the isothermal reversible process. Now suppose you have not given the terms in the V2 or V1 terms. Okay, you will have not given V2 and V1. You have given the pressure terms. Then what you have to do? You know that P1 V1 is equal to P2 V2. Okay, so you can write P1 upon P2 will be equal to V2 upon V1. This thing we know. Okay, so we can write here W is equal to minus 2.303 nRT logarithm of P1 upon P2. Okay, so you can also use this formula if you have not given the values of volume and you have given the pressure terms, then you will use this formula. Now suppose you have not given nRT, you does not know the value of nRT, then what you can use? You can use minus 2.303. Either you can put here the value of P1 V1 or you can put here the value of P2 V2 and you can write log either V2 of V1 or you can write P1 upon P2. Anything you can write. Okay, so you can write in this manner. In both the ways you can write here. All the formulas are applicable. Okay, so these are the different formulas for the reversible process. Alright, now see the work done. for an ideal gas in the case of isothermal irreversible process. Okay, always remember we are talking about the ideal gas, we are not talking about the van der Waals gases. Okay, so suppose first of all we are seeing the intermediate condition. Okay, this is for the intermediate condition. Intermediate condition means suppose our process is doing expansion. It is going from V1 to V2. Initial volume is V1 and final volume is V2. It is changing and this is done at a constant external pressure. It means our external pressure is constant. Okay, always remember whenever you have given that the system is doing work under a constant external pressure, then you should remember this thing is for the irreversible process. Whenever you have not given irreversible process and you have given that the external pressure is constant, then it means that it is an irreversible process. Okay, so constant external pressure means irreversible process. Okay, and it's, see here, this external pressure, its magnitude will be always less than the pressure of the gas. It means suppose this is, see here, this is our system. Okay, and this is going from a state that is at the volume V1 to a state that is at the volume V2. It means it is doing expansion. Okay, here is the external pressure. We are doing here, we are putting here external pressure. Okay, this external pressure will always be lesser than the pressure of the gas. It means if here the gas is at the 4 atmosphere, then this external pressure is always less than this 4 atmosphere. It may be 3 atmosphere, it may be 2 atmosphere, but it cannot be 4 atmosphere. Okay, when it will be equal to 4 atmosphere, then there will be no expansion. Okay, so the external pressure is always lesser than the pressure of the gas. Now this external pressure is constant, so W will be equal to what we can write. This is the formula, integration of PdV. Okay, but our pressure is constant, so we can put here outside P external and integration of dV between the limits V2 to V1. Okay, so this will be equal to minus P external V2 minus V1. Okay, so we can write W is equal to minus P external V2 minus V1. This is the formula for the irreversible process. Work done in the irreversible process. Okay. Now, suppose you have not given V1 or V2. Then what will you do? You will replace it. V2 will be equal to nRT upon P2. Okay. Similarly, V1 will be equal to nRT upon P1. So we can replace it by this. So don't get confused. Just use the ideal gas equations and you can find the question's answer. So write here nRT upon P2 minus nRT upon P1. Or you can take this outside. So what you are getting, W is equal to nRT P external 1 upon P1 minus 1 upon P2. Okay, so these are also the formulas for the irreversible process. Okay, you can use any of the formula, you will get your answer. The second type of the work in the irreversible isothermal process is work done in free expansion, or we can say it work done in vacuum. In both these cases, the external pressure is equal to 0. Okay, suppose we are seeing here a system. Okay, and there is pressure on this piston. Okay, suppose this pressure is 3 atmospheric pressure. Okay, and suddenly we are removing this pressure. We are doing this 3 atmospheric pressure is equal to 0. It means suddenly we open this piston. Okay, and now this gas will be like that, in this manner. This is free to move anywhere. Now it can move anywhere. We call it the work done in the vacuum or work done in the free expansion. In both these cases, the pressure is equal to 0. So the work done will be equal to minus P V2 minus V1 we know, and P is equal to 0. So work done will be equal to 0. So nothing to remember, just only you will have to remember one thing, that whenever you have given that there is no external pressure, or the work is done in the vacuum, or work is done in the free expansion, then in that case the work will be equal to 0. Okay. Now the next thing that you will have to find out is the calculation of del U. First of all, we have seen the work done in the isothermal process. Now you have to calculate the internal energy change in a isothermal process, because whenever the question is asked, you have also asked about the isothermal process internal energy change. So you should know. See here, this is very simple. We know that our process is isothermal. So in isothermal process dt is equal to 0. It means there is no change in the temperature. And we know that this U, it means change in the internal energy, is a function of temperature. And when temperature changes 0, it means del U is automatically equal to 0. Okay, so whenever you have given the isothermal process, always remember that the change in internal energy will be equal to 0. Okay, now the next thing is the calculation of del H. It means change in the heat capacity. For this, you know what is the formula? Del H is equal to del U plus del PV. Or you can write del U plus del Ng RT. Here, what is del G? Del Ng. Del Ng is the change in number of moles of gaseous molecules. Okay, only we have to consider the gaseous molecules. Okay, and RT we know this is gas constant and temperature, and del U we already have it taken here, so we can find out the value of del H. Okay, now the next thing is the calculation of Q. Q means heat change, and this we can find out from our formula of first law of thermodynamics. Del U is equal to Q plus W. So we know about the del U, this is equal to 0. Okay, so Q will be equal to minus W. So once we know the value of W, we can find out the value of Q. Okay, so in this way, we can understand, we can find out all the 4 variables that we need. Okay, now the important thing is how to deal with the questions, how to solve the numericals. That is the important thing. Okay, so that we will see in our next lecture. First of all, learn all the formulas, then we will solve the numericals. So stay with us. If you are liking videos, please like them, please share them, please comment to me. Thank you.